Dear students, welcome to today's class. In last two classes onwards, I am explained what is a relation, domain of a relation, range of a relation, codomain of a relation, and we did some problems on relations also. Okay, in this class, I am going to explain what are the different types of relations. So, we have the relations as a void relation or empty relation, universal relation, identity relation, reflexive relation, symmetric relation, anti-symmetric relation, transitive relation and equivalence relation. So, let us discuss these relations one by one. Dear students, let us discuss what is a void relation and a universal relation. This void relation is also known as empty relation. Void set, just now in the set theory we know what is a void set, means a set containing no elements. This is also void relation. A relation having no ordered pairs is called a void relation. It is denoted by null set. Okay, now for example, if A is a set, you have taken 1, 2, 3. Okay, so what is the void relation here? So your void relation is this. So this is your void relation. That means the relation does not contain any ordered pairs. This is called the void relation. Now we have a very important note point, that is void relation is the smallest relation on A. Smallest relation on A. It is a very smallest one. Why? Because there is no ordered pairs in that. So this is a void relation. So it is the smallest relation on a set A. On a set A, how many relations we will get? We have different types of relations. Set 1, set 2, set 3, on A means A cross A, that is 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 1, 3, 3, like that we will get. So from this ordered pairs which contains only one element, that means 1, 1, 1, 2, 1, 3, all those from this, out of which a relation which containing no elements is called a void relation, which is the smallest one. Coming to universal relation, let A be a set, then A cross A is called the universal relation, which is the biggest relation, largest relation on A. So on the whole, from void relation, universal relation, I will explain taking one example. Okay, now right. So let us take one example. Let A is equal to 1, 2. Now what is the relation in A means what? R is subset R equal to A cross A. Now what is A cross A? What is A cross A is 1, 1, 1, 2, 1, 1, 1, 2, 2, 1, 2, 2. This is a relation. Okay. So this is the largest relation. This is the largest relation. Understand? What are the remaining relations? So we have different types of relations. Set 1, 1, it is a relation. Set 1, 2, it is a relation. Set 1, 1, 1, 2, it is a relation. Set 1, 1, 1, 2, 2, 1, 2, 2, it is also a relation which is the biggest relation. So this is the universal relation, and R is equal to a relation which containing no elements. It is a void relation. So while studying these two things, so you comparatively study. First study the void relation, learn the void relation, and afterwards learn universal relation. Both are quite opposite. It has no element. The universal will have all possible elements, all possible ordered pairs, 1, 1, 1, 2, 2, 1, 2, 2, all possible ordered pairs across the universal relation will have. Understand this? So void relation is a quite opposite of universal relation. Okay, I hope that you understand this concept. So let us see the remaining relations. Now I am going to explain about identity relation and reflexive relation. So try to understand the difference between identity relation and reflexive relation. these two generally students will get confused by they both think that both are same, but both are not same. Try to understand this. Let A be a set, okay, any set. Then the relation A comma A, where A belongs to the set A, is called the identity relation on A, and it is denoted by I suffix A. So that means if A is a set 1, 2, 3, the identity relation means what here? 1, 1, 2, 2. Yes, here A, that's all. He is not saying that for all elements should belongs to that relation. Say here, if it is A, one element is there such that A, A also should be in that relation. That is 1, 1 should be in identity relation. 2, 2 is also there. That's why this relation is called identity relation. Clear? Now, coming to reflexive relation, here you observe here one word. A relation or on a set is said to be reflexive if every element of A, that is a very, very important, every element of A is related to itself. Every element of A is related to itself. That is, if R is reflexive, then A comma A belongs to R. This is what the meaning of this symbol. For all A belongs to A. That means what? If A is a set 1, 2, 3, then R is a reflexive relation means what? Here, what is the first element? 1. 1, 1 should be in that. 2, 2 also should be in that. 3, 3 also should present in that relation. For all A belongs to A. Here no need. Here no need. Understand the difference between the identity relation and reflexive relation. Then from this we can say that all reflexive relations are identity relations, but all identity relations need not be reflexive relations. For example, I will tell one example. For example, this is identity relation, but it is not a reflexive relation. Why? Because the element 3 belongs to A, but it does not belongs to the relation. Understand this? That's why it is simply an identity relation, but not a reflexive relation. Right. In our geometry, what are the relations which are reflexive? In geometry, if you observe, in geometry, parallel to, the relation parallel to is reflexive relation. How can you say? Every line is parallel to itself. Every line is parallel to itself. Therefore, parallel to is a reflexive relation, is similar to, every triangle is similar to itself. It is a reflexive relation. Congruency, that means every triangle is congruent to itself. Every line segment is congruent to itself. Every regular polygon of n sides is of equal sides is a congruent to itself. Understand? So parallel, similar, congruent, all these are similar reflexive relations in the geometry part. Coming to in number theory, so for example, is equal to, this relation word is equal to is a reflection relation. Why? 2 is equal to 2. 2 is equal to 2. That means every number is equal to itself. Therefore, is equal to, the word is equal to is a reflexive relation. Is a factor of, that means what? Every number is a factor of itself. 4 is a factor of 4. 5 is a factor of 4. Multiple of is a multiple of, that means every number is multiple of itself. That's why is a factor of, is a multiple of, is equal to, all are reflexive relations in the set of real numbers. Understand? So here these are for geometrical examples, and these are all examples from the number theory. Okay, now I hope that you understand these two concepts. Let us see the next thing. Dear students, let us see two more types of relations. The first one is a symmetric relation, another one is anti-symmetric relation. So these two are like together. So whenever you are learning the relations, you try to learn these two simultaneously. The first one is symmetric relation. A relation R on a set is said to be a symmetric relation if and only if A comma belongs to R, then B comma A also belongs to R. For all A comma B belongs to R. So to make you understand this definition, I will tell a very easy example. Let us take two lines L and M. L is parallel to M. L is parallel to M. Is it not that M is also parallel to L? If L is parallel to L, is it not that M is also parallel to L? Yes. That means if L is related to M, then M is also related to the same way as L. Then that relation, what is the relation here? Parallel to, is a symmetric relation. Like that, perpendicular. If L is perpendicular to M, then M is also perpendicular to L. Understand this? So therefore, perpendicular in the set of, in the domain of geometry, perpendicular where we will see in between two lines. So if L is perpendicular to M, then M is also perpendicular to L. Therefore, perpendicular is a symmetric relation. But sir, tell me one example which is not symmetric. Yes, I will tell. 2 divides 4. Yes, 2 divides 4. Everybody knows that 2 divides 4. But is 4 divides 2? No, wrong. 2 divides 4, but 4 does not divide 2. Example, the best example. 3 is a factor of 9. 3 is a factor of 9, but 9 is not a factor of 3, whereas 9 is a multiple of 3. Therefore, factor of is not a symmetric relation. That is, the relation between 3 and 9 is what? Factor. But the relation between 9 and 3 is multiple. Understand? So, that is not a symmetric relation. That means here you see here 2, 4 belongs to R, such that 4, 2 also should belongs to R. Understand? So here also 4, 6 belongs to R, therefore 6, 4 also should belongs to R. Understand this? Understand this concept? That means, so while checking symmetric relation, you have to take any two quantities, any two distinct quantities, whatever may be these distinct quantities, maybe two lines, maybe two triangles, maybe two numbers, whatever may be that. Understand? If A is related to B, in whatever may be the manner, the same relation should be there from B to A. Then that relation, what is the relation between them, is called symmetric relation. Understand this? Right. Coming to anti-symmetric relation, just like symmetric relation only, but here the thing is, let A be any set, a relation or on a set is said to be anti-symmetric relation if and only if both same, if A should be related to B and B also should maintain the same relation with A, but these two should be equal. That implies whenever if A is related to B and B is related to A, if at all if these two quantities are equal, then that relation is called anti-symmetric. Here no need to here no need to A is equal to B. For example, see here 2, 4 belongs to R, 4, 2 also belongs to R, but 2 is not equal to 4. That is the only symmetrical. If at all if it is 2 is equal to 4, then that relation is anti-symmetric relation. So one more very important point is here is, in anti-symmetric relation, if A, B belongs to R, but B, does not A belongs to R, then still it is a anti-symmetric relation. We can call it as an anti-symmetric relation. That means what? No need of these two relations must end this A, B and B, A. Sometimes if B, A also does not belongs to R, then still we can say that it is an anti-symmetric relation. For example, I will tell one example. For example, X divides Y and Y divides X. X divides Y and Y divides X. It is not a symmetric relation. If X divides Y and Y divides X, is it not X is equal to Y? Is it not X is equal to Y? Therefore, divides X divides Y and Y divides X. Therefore, divides is a anti-symmetric relation, whereas divides is not a symmetric relation. Understand? If at all, if X divides Y, it is no need that Y is divides X. If at all, if X divides Y and Y divides X, then when it is possible, when X is equal to Y. Therefore, divides is an anti-symmetric relation. Understand that? So, try to read these two topics simultaneously, so that you can easily understand. Okay, now I hope that you understand this concept. So let us go for next concept. Dear students, let me explain about this next type of relation, that is transitive relation. Next one, equivalence relation. So before explaining this transitive relation, let me give one example. Okay, there are three lines are there. L is parallel to M, M is parallel to N. Observe here, L is parallel to M and M is parallel to N. Is it not that L is parallel to N? Is it not right that L is parallel to N? Yes, anybody can say. That means the relation between L and M is what? Parallel. What is the relation between M and N? Parallel. Therefore, L is also related to N. Same how L and M are related and M and N are related, the same way L and N are also related like that. So this relation parallel to is a transitive relation. So in order to check the transitive relation, you have to take any three quantities, either three lines, three triangles, three numbers, like that. So let me tell one more example. 2 divides 4, 4 divides 8. Is it not 2 divides 8? Yes, right. 2 divides 4, anybody knows. 4 divides 8. Yes, automatically 2 divides 8. Therefore, divides is a transitive relation, right? Let me check, is it perpendicular to is a transitive relation. Let us see here, there is a line, L is perpendicular to M, M is perpendicular to N. L is perpendicular to M and M is perpendicular to N. Is L is perpendicular to N? No, definitely L will be parallel to N. That means between the relation L and M, the relation is perpendicular. Between M and N, the relation is perpendicular. But from L and N, the relation fails. Therefore, perpendicular is not a transitive relation, but whereas it is a symmetric relation. L is perpendicular to M and M is perpendicular to L. But it is not an anti-symmetric relation. Why? L is perpendicular to M, M is perpendicular to L, but L cannot be equal to M. Understand? Okay, right. So coming to the definition point of view, like in a geometry also, similar to is a transitive relation. Congruence to is also transitive relation. Perpendicular to is not a transitive relation. Divides is a transitive relation. Factor is a transitive relation. 2, 3 is a factor of 6. 6 is a factor of 12. Therefore, 3 is also a factor of 12. Understand? Therefore, factor of is also a transitive relation. So, in order to check reflexive relation, you have to consider one item, one line, one triangle, one number. For to check symmetric relation, you have to take two items, two lines, two triangles, two numbers, whatever may be that. To check the transitive relation, you have to consider any three items, any three numbers, any three lines, any three triangles, anything, any three, whatever may be that. To check transitive relation, we have to take any three items. First, to whatever may be the relation, you see the relation between first and the second one, and the second one and third one also same relation maintains. If the relation, same relation should maintain from A to C, then only that relation we call it as a transitive relation, otherwise it is not a transitive relation, right? Coming to equivalence relation, so it is nothing to learn more. So it is a relation is a reflexive, symmetric and a transitive, then that relation is called an equivalence relation. The best example is parallel to. Parallel to is a equivalence relation. Why? Every line is parallel to itself, reflexive satisfies. If L is parallel to M, M is parallel to L, yes, it is a symmetric relation. L is parallel to M, M is parallel to N, and L is parallel to, this is a transitive relation. That means parallel to is a equivalence relation, similar to is an equivalence relation, congruence is an equivalence relation, divides is not an equivalence relation. Why? Because 2 divides 2. Yes, it is reflexive. 2 divides 4, but 4 does not divide 2. Therefore, symmetric fails, but transitive satisfies. And like that, factor of also. So 2 is a factor of 2. Yes, right. If 2 is a factor of 3 is a factor of 4, 4 is a factor of, but 4 is not a factor of 2. Symmetric fails. That means if a relation is a reflexive, symmetric and transitive, then that relation is called equivalence relation. Understand this? So in this class, today's class, we have seen the types of relation. So the first one is a reflexive relation, next one symmetric relation, first one void relation, universal relation, reflexive relation, identity relation, symmetric relation, anti-symmetric relation, transitive relation and equivalence relation. So these are the types of relations that we discussed today. So basing on these relations, in the next class we are going to see the number of relations, how many reflexive relations, how many transitive relations, how many equivalence relations. So that type of number of relations, those formulas are there. Those formulas I will explain in the next class, and some more problems which are given in the previous JEE mains examinations, various competitive examinations problems are also I will discuss in the next class. So until then, all the best.